Try to think in the year 2124, as humanity marks 100 years of living on Mars of the moment. We realize that the people born there will never return to Earth because bodies shaped by Mars's gentle gravity cannot survive our planet's crushing pull. From birth, they grow adapted to thin air, weak gravity, and an environment hostile every second of every day. At that point, the question is whether a species evolved for blue skies and rain can endure life away from them at all. If you want to understand where this path leads, subscribe to learn more. To understand what this means, we need to understand gravity not as background physics, but as the invisible sculptor of everything we are. On Earth, 1g, 1 times Earth's gravity, pulls blood from your feet to your brain every heartbeat. It keeps your bones dense by making them bear weight constantly. It maintains your muscle tone just by making you stand up. We never think about it like fish don't think about water. But step away from it and your body begins to dismantle itself. We know this from astronauts who've spent months on the International Space Station. They lose 1 to 2% of their bone density every month in near weightlessness. After 6 months in space, their bones have the density of an 80-year-old's. Exercise helps, but can't fully compensate, because you're not just missing occasional stress on your bones, you're missing the constant 24/7 pull that shaped your skeleton from birth. NASA has documented this extensively through studies on astronauts from the 1960s through today. Scott Kelly, who spent 340 days on the ISS from 2015 to 2016, lost significant bone density despite exercising 2 hours every day. Think about what this means at a cellular level. Your bones are living tissue constantly rebuilding themselves. Cells called osteoblasts build new bone. Cells called osteoclasts break down old bone. In normal gravity, these processes balance perfectly. The stress of bearing your weight tells your body through mechanotransduction, the conversion of mechanical signals into biochemical responses, that bone density needs to be maintained. In microgravity or low gravity, that mechanical signal disappears. Your body's cellular machinery interprets the absence of loading as we don't need this bone anymore and begins breaking it down faster than it rebuilds. Mars has 0.38 g, roughly a third of Earth's gravity. Stand on Mars and you'd feel light, almost bouncy, like every step wants to launch you into the air. Sounds fun for 10 minutes. Over 10 years, it's devastating. Your heart, not needing to pump blood uphill against full gravity, anymore weakens. The heart is a muscle, and like all muscles, it responds to the mechanical demands placed on it. Reduce those demands consistently, and the heart undergoes what physiologists call cardiac atrophy. The heart muscle literally shrinks because it doesn't need to work as hard. Your bones, not bearing their full designed weight, leach calcium into your bloodstream at an accelerated rate. That calcium has to go somewhere. In astronaut studies, researchers have found increased kidney stone formation. The excess calcium crystallizes in the kidneys. There's also concern about calcium deposits forming in blood vessels, potentially increasing cardiovascular disease risk. Your muscles atrophy because there's no resistance. The postural muscles that keep you upright on Earth, your calves, your thighs, your back muscles, don't have to work nearly as hard on Mars. And no exercise routine can replace full gravity. Astronauts on the ISS exercise 2 hours per day with specialized equipment resistance bands, treadmills with harnesses that pull them down to simulate weight stationary bikes. It helps, but it doesn't prevent bone loss entirely. You can work out 2 hours a day, but gravity works on you 24 hours a day. It's not just about strength training. It's about the constant mechanical loading that tells your cells how to organize themselves, how to build structure, how to maintain integrity. Studies from the ISS between 2000 and 2024 show that drugs like bisphosphonates can slow bone loss. These drugs work by inhibiting osteoclasts, the cells that break down bone, but they have significant side effects: nausea, muscle pain, jaw problems, and paradoxically increased fracture risk if you stay on them too long because they prevent normal bone remodeling. And we're talking about decades of use for Mars colonists, not the months or few years that astronauts spend in space. The long-term effects of bisphosphonate use for 20 or 30 years aren't fully understood because we don't have Earth-based populations taking them for that long. The math is simple and brutal. After 10 years on Mars, based on ISS data, Extrapolated to 0.38 G environments, your bones would resemble those of a 70-year-old on Earth. After 20 years, your fracture risk climbs into dangerous territory. You don't recover from this. Bone loss in microgravity is partially reversible. Astronauts regain some bone density when they return to Earth, though not all of it. But on Mars, there's no returning to normal gravity. You're in 0.38 G permanently, which means the bone loss might stabilize at some lower level, but you'll never have Earth normal bone density again. But it's not just bones and hearts. Your entire vascular system, the network of blood vessels throughout your body, has adapted over millions of years of evolution to work in 1G. Your blood pressure is calibrated for 1G. The baroreceptors in your carotid arteries and aortic arch that regulate blood pressure are tuned to detect pressure changes in 1G. The fluid distribution in your body depends on 1G pulling fluids downward. In microgravity, astronauts experience what researchers call fluid shift blood, and other fluids move from the lower body to the upper body and head because there's no gravity pulling them down. Their legs get skinnier as fluid leaves. Their faces swell as fluid accumulates. The increased fluid pressure in the skull causes vision problems, a condition called spaceflight-associated neuroocular syndrome, or SANS. Studies show that about 40% of astronauts on long-duration missions develop measurable vision changes. The optic nerve swells. The back of the eyeball flattens. Some astronauts have needed glasses for the first time after returning from space. On Mars with 0.38 G, the fluid shift wouldn't be as extreme as in microgravity, but it would still occur. You'd still have more fluid in your upper body and head than evolution designed for. This could cause chronic vision problems, chronic sinus congestion, chronic headaches. And these wouldn't be temporary adjustment problems, they'd be permanent features of living in low gravity. Your inner ear, which controls balance through the vestibular system, would be confused constantly. The vestibular system evolved to work in 1G. The otolith organs, the utricle and saccule, contain tiny calcium carbonate crystals that move in response to gravity and acceleration. These movements are detected by hair cells that send signals to your brain about which way is up and how you're moving. In 0.38 G, these crystals would move differently. Your brain would receive signals that don't match what it expects, based on 300,000 years of human evolution in 1G. You'd feel mildly dizzy for months until your brain recalibrated. Some people might adapt fully. Others might never fully adjust, suffering from chronic spatial disorientation. They'd live their entire lives feeling slightly off balance, slightly wrong in a body that doesn't quite work the way evolution designed it. Now, here's where it gets profound and irreversible. That first generation born on Mars will develop differently from conception. Their bones will form in 0.38 G, which means the mechanical stresses during development will be completely different. Bone development in the fetus and infant is highly responsive to mechanical loading. When a baby kicks in the womb, when a child takes their first steps, the mechanical forces shape how bones grow and calcify. A child developing entirely in 0.38 G will have bones that are lighter, less dense, and structured differently than Earth bones. They'll be perfectly adapted to Mars gravity, but perfectly adapted to Mars means catastrophically maladapted to Earth. By the time they're adults, their skeletal structure will be fundamentally incompatible with Earth gravity. Based on what we know about bone development and adaptation, a Mars-born adult brought to Earth would likely experience immediate skeletal stress fractures from trying to bear their own weight in full gravity. Their heart, having never worked against full gravity, would struggle to maintain adequate blood flow to the brain. They would likely experience syncope, fainting within minutes of standing. Even lying down, the increased weight of their body pressing against their spine could cause vertebral compression fractures. This isn't speculation based on science fiction. This is extrapolation from solid physiological data about how bones and cardiovascular systems respond to gravitational loading. The data comes from decades of studying astronauts, from bed rest studies that simulate some effects of microgravity, from patients with conditions that reduce mechanical loading on bones. By generation 10 or 15, Martian humans will be a new subspecies in all but name physically incompatible with Earth. They'll be taller without full gravity, compressing the spine, and limiting bone growth, humans on Mars would likely grow several inches taller on average. Their bones will be lighter and more fragile, by Earth standards perfectly adequate for Mars, but completely insufficient for Earth. Their hearts will be adapted to pumping against 0.38 G, unable to handle the workload of 1 G. They'll think of Earth the way we think of Jupiter, a place with crushing gravity where humans can't survive. And they'll be right. The planet humans evolved on will have become uninhabitable for their subspecies. After 20,000 years, after 800 generations, there won't be one human species spread across the solar system. There will be multiple human subspecies, each adapted to their local gravity, each unable to visit other colonies without dying. This is the gravity problem. This is what 0.38 G means over deep time. It's not a difficulty to overcome. It's a fundamental constraint that will shape human evolution across the solar system. We can manage it with engineering rotating habitats that simulate 1 G through centrifugal force. Though these are expensive and complex. We can manage it with medicine, drugs, and exercise regimens that slow bone loss, though they can't prevent it entirely. But we can't eliminate it. The gravity you're born in becomes the gravity you're trapped in. And over 20,000 years, that means humanity doesn't spread across the solar system as one species. It fragments into multiple species, divided by the invisible walls of gravitational incompatibility. But even if we accept that Martian humans will be biologically different from Earth humans, there's a more fundamental question, one we haven't answered because we can't ethically test it. Can humans even reproduce successfully off Earth? Right now, we have zero data on human pregnancy in space. None. Not one documented case of human conception, gestation, or birth in reduced gravity or microgravity. What we have are mammal studies primarily with mice and rats, and the results are deeply concerning. Pregnant mice sent to the ISS show miscarriage rates approximately 50% higher than control groups on Earth. The offspring that do survive gestation often have significant problems. Weaker bones, underdeveloped muscles, vision abnormalities, and developmental delays in motor function. A 2019 study, published in the journal PLOS, sent frozen mouse embryos to the ISS, thawed them in orbit, and observed their development. The embryos showed abnormal cell division patterns. A 2021 study found that pregnant mice exposed to simulated Martian gravity using a centrifuge to create 0.38 G had offspring, with reduced bone density and muscle mass compared to controls born in normal gravity. But mice aren't humans. Mice gestate for approximately 3 weeks. Human pregnancy lasts 9 months, 13 times longer. Mice weigh less than 30 grams at birth. Human babies weigh 3 to 4 kilograms, over 100 times heavier. The scaling issues alone make direct extrapolation problematic. More importantly, mouse brains are fundamentally simpler than human brains. A mouse brain contains roughly 71 million neurons. A human brain contains approximately 86 billion neurons, over 1,000 times more. The human cerebral cortex, responsible for higher cognitive functions, is vastly more complex and requires much more precise developmental conditions. We simply cannot assume that mouse pregnancy data translates directly to humans. Here's what we know about human gestation from Earth-based physiology. It evolved under 1 G over millions of years of mammalian evolution. The fetus develops in a specific orientation inside the uterus. In normal pregnancy, the fetus is head down for most of the 3rd trimester, positioned by gravity. Amniotic fluid surrounds the fetus, and its distribution is affected by gravity. The placenta attaches to the uterine wall in locations partially determined by gravitational blood flow patterns. Fetal bones begin calcifying in the 1st trimester and continue through birth. This calcification process is mechanically sensitive bones form in response to the stresses they experience. In 1 G, the fetal skeleton experiences consistent gravitational loading throughout development. The long bones, femurs, tibias, humeri form with density appropriate for the gravity they're developing in. The fetal brain develops through a complex process where neural stem cells migrate from deep brain structures to the outer cortex. This migration creates the layered structure of the cerebral cortex. Studies of brain organoids, lab-grown miniature brain tissues sent to the ISS show that in microgravity, neural cell migration patterns are disrupted. The cells don't form proper layers. The research published in Stem Cells Translational Medicine in 2020 suggests that the physical forces of gravity play a role in guiding neural development, not just chemical gradients as previously thought. The fetal cardiovascular system develops in response to gravitational fluid dynamics. The heart begins beating at week 5 of gestation. Blood flow patterns through the developing heart chambers are affected by gravity. The major blood vessels, aorta, vena cava, pulmonary arteries, form with geometries optimized for 1G blood flow. In reduced gravity, these flow patterns would be different, potentially leading to different vessel geometries or valve formations. Now, here's the problem. We can't test any of this with humans. The ethical barriers are absolute and appropriate. No institutional review board would approve an experiment involving human pregnancy in space. The risks are unknown and potentially catastrophic. You can't knowingly put a developing fetus at risk just to gather data. The Declaration of Helsinki, which governs medical research ethics, forbids research that poses significant risk to subjects without reasonable expectation of benefit to that subject. A space pregnancy would pose enormous unknown risks to the fetus with zero direct benefit. So that first Mars pregnancy will be an uncontrolled experiment. Some couple, probably young colonists in their 20s or 30s, will decide to start a family. They'll conceive on Mars, either naturally or through assisted reproduction. Then comes 9 months of unprecedented uncertainty. Every prenatal checkup becomes a potential discovery of the unknown. Every ultrasound is scrutinized not just for normal developmental milestones, but for any deviation that might indicate low gravity effects. Medical staff would be looking for things no one has ever seen before. Are the fetal bones forming with adequate density? Is the brain developing properly? Is the heart forming correct valves and chambers? Is the placenta functioning normally? They'd be comparing measurements to Earth normal values. But those values might not apply. What's normal for Mars gravity might be very different from Earth normal, but we won't know until we see it. The psychological burden on those first Mars parents would be immense. They're not just having a baby, they're testing whether human reproduction is possible off Earth. Their pregnancy is being documented, measured, analyzed. Scientists on Earth and Mars are watching their data. If the pregnancy fails, if the baby miscarries, or is stillborn, or is born with severe problems, they'll know their loss is providing data that will shape humanity's future. That's an enormous weight to carry on top of the normal anxieties of pregnancy. And if the pregnancy fails, if human fetuses simply cannot develop properly in 0.38 G, then there is no 800 generations. There's one generation of colonists who age and die without descendants. Mars becomes a place humans visit for work assignments like an Antarctic research station, but never a place where humans put down roots and build a civilization. Some reproductive biologists are cautiously optimistic. They point out that mammalian reproduction is remarkably robust. Species have adapted to reproduce in wildly different environments on Earth, from Arctic conditions to tropical heat, from high altitude to sea level. They suggest that human reproduction might work in low gravity with some medical support, perhaps monitoring for complications, perhaps medical interventions during critical developmental windows. Other scientists are pessimistic. They point out that all terrestrial reproduction evolved in 1G. It's not just an environmental parameter we adapted to. It's a fundamental constraint that shaped the entire developmental program of vertebrate embryology over 500 million years. Changing gravity isn't like changing temperature or humidity. It's like changing one of the basic physical constants the developmental program assumes. And developmental programs are notoriously sensitive to disruption. Small changes in developmental conditions can have catastrophic effects. The moderate view is that we simply don't know, and we won't know until we try. The first few Mars pregnancies will tell us a lot. If they proceed normally and produce healthy babies, that's enormous evidence that human reproduction can work off Earth. If they fail consistently, we'll know that Mars colonization as traditionally imagined isn't possible, at least not without artificial gravity technology that simulates 1G during pregnancy. The stakes could not be higher. 20,000 years requires generation 2 to be born successfully, then generation 3, then 4. 800 times in a row across 20,000 years without catastrophic fertility failure. If humans can't reproduce successfully on Mars, or if fertility declines each generation due to accumulated low-gravity effects, then the entire project of space colonization fails within a century or two, not over millennia. One break in that reproductive chain, and everything ends. We're not just asking if we can survive in space, tolerate the low gravity, manage the radiation, handle the isolation. We're asking if we can biologically reproduce there, generation after generation after generation, without the gravitational field that shaped every aspect of human development for our entire evolutionary history as vertebrates. We're asking if 300 million years of evolution in 1G can be overridden by 9 months of development in 0.38G without breaking something fundamental in the developmental process. We're asking if human babies can form properly when fluid dynamics are different, when mechanical stresses are reduced, when the physical forces that guide cellular organization are altered. And we're asking this question knowing that the answer won't come from laboratory studies or computer simulations. It will come from real pregnancies, real fetuses, real families taking risks that we can't fully quantify. The first Mars baby will be born into history as either proof that humanity's future in space is possible, or as a tragedy that reveals our biological limits. This is the fertility unknown, the foundation on which all of 20,000 years rests. And it's a foundation we can't inspect, can't test, can't verify until we build on it and see if it holds. Meanwhile, there's another threat that compounds the fertility question, one that's invisible and constant, and slowly destroys cellular integrity radiation. On Earth, we live under two shields that block most cosmic radiation. The first shield is Earth's magnetic field, called the magnetosphere. Generated by convection currents of molten iron in Earth's outer core, this magnetic field extends approximately 60,000 kilometers into space. Charged particles from the sun, the solar wind, hit this magnetic field and get deflected around Earth. Some particles spiral down magnetic field lines toward the poles, where they hit the upper atmosphere and create auroras. The magnetosphere stops most solar radiation from reaching Earth's surface. The second shield is Earth's atmosphere. At sea level, you have approximately 10 metric tons of air above every square meter of your body. That's the weight, creating 14.7 pounds per square inch of atmospheric pressure. All that air acts as shielding. Cosmic rays, high-energy particles from outside the solar system, hit air molecules in the upper atmosphere. The collisions create cascades of secondary particles, but most of those particles are absorbed by more air before they reach the ground. Together, the magnetosphere and atmosphere block 99.9% of space radiation. The result is that on Earth at sea level, the average person receives about 0.3 rem of radiation exposure per year from all sources, cosmic rays that make it through radon gas from rocks, trace radioactive elements in food and water, medical X-rays if you get them. That's the baseline. Your cells have evolved with DNA repair mechanisms calibrated to handle this level of background radiation. You get some DNA damage every day from radiation and other sources, and your cells fix most of it. The repair mechanisms are good but not perfect, which is why cancer risk increases with age, accumulated unrepaired damage over decades. Step into space, and the radiation environment changes dramatically. The ISS orbits at 400 kilometers altitude, still within Earth's magnetosphere. Astronauts on the ISS receive approximately 15 rem per year, about 50 times Earth's background radiation. That's considered the upper limit of acceptable exposure for radiation workers on Earth. NASA has set astronaut career limits based on age and sex that range from 40 to 300 rem total career dose, depending on how that exposure translates to cancer risk. Mars is vastly worse. Mars has no magnetic field. The planet's core solidified billions of years ago, stopping the geodynamo that would generate a magnetic field. Mars's atmosphere is only 0.6% as thick as Earth's, barely any shielding at all. The result is that on Mars's surface, radiation exposure is approximately 50 to 60 rem per year. That's 200 times Earth's background level and 4 times what ISS astronauts receive. This radiation comes from multiple sources. Galactic cosmic rays are high-energy particles, mostly protons, accelerated to near light speed by supernova explosions and other violent cosmic events. They've been traveling through space for millions of years. When they hit Mars, they hit you. A single cosmic ray passing through your body can strike DNA, directly breaking chemical bonds and causing double-strand breaks, the most dangerous type of DNA damage. Solar energetic particles are bursts of radiation from the sun during solar flares and coronal mass ejections. These events are somewhat predictable. Solar activity follows an 11-year cycle, with solar maximum being more active than solar minimum. But individual events are unpredictable. A solar flare can erupt with minutes of warning, sending a burst of high-energy protons toward Mars. During a major solar particle event, radiation levels can spike to dangerous levels. The February 1956 solar event, if it had occurred while astronauts were on the Moon or Mars, would have delivered a potentially lethal dose to anyone caught outside. Now, you might think just build thicker walls, put more material between you and the radiation. But here's the paradox that makes space radiation particularly insidious. Thick aluminum walls, what spacecraft are typically made of, stop low-energy particles but create problems with high-energy ones. When a galactic cosmic ray traveling at 99% light speed hits an aluminum nucleus, the collision shatters both nuclei in a process called spallation. The result is a spray of secondary particles, neutrons, alpha particles, nuclear fragments traveling in all directions. These secondary particles can be more biologically damaging than the original cosmic ray. The phenomenon is called secondary radiation production, and it's a major problem for spacecraft shielding. You're trying to stop radiation, and you're creating more of it. NASA research published in 2018 showed that for galactic cosmic rays, aluminum shielding thickness has an optimum about 10 centimeters. Thinner than that, and too much primary radiation gets through. Thicker than that, and you're creating more secondary radiation than you're blocking primary. The best shielding materials are hydrogen-rich substances. Water is excellent. Hydrogen nuclei are light and absorb energy without creating many secondaries. Polyethylene plastic also works well. The problem is mass. Water is heavy. To shield a habitat effectively, you need several meters of water or polyethylene. That's enormous mass to transport to Mars or manufacture there. The most practical solution for Mars is to use local resources. Martian regolith, the dirt and rock on the surface, is free and plentiful. Studies show that 3 to 4 meters of Martian regolith provides good radiation shielding. But that means your habitat needs to be buried or built like a bunker with meters of dirt piled on top. You're not living in a habitat with windows and views. You're living in a cave lit by artificial lights, buried under Martian soil for protection. So Mars colonists face a constant trade-off. Deep buried habitats, where radiation exposure is minimized, but living spaces are cramped, dark, and psychologically oppressive. Or thinner walled surface habitats, with windows and space and light, but higher radiation exposure. Most colony designs compromise deeply buried residential and sleeping quarters, where people spend nights and recreation time connected to thinner walled workspaces, where people spend limited hours during the day. But even with good shielding, you can't eliminate radiation exposure on Mars. You accumulate dose every time you go outside for EVA work. You accumulate dose in the thinner-walled sections of habitats. You accumulate dose during solar particle events if you're caught away from shelter. Over years and decades, the dose adds up. Let's talk numbers based on current NASA exposure projections. A Mars colonist with reasonable shielding and precautions would accumulate approximately 50 rem per year. After 1 year, that's 50 rem total, same as NASA's annual limit for astronauts. After 10 years, 500 rem. After 20 years, 1,000 rem. Your lifetime cancer risk, which starts at about 40% for the average person on Earth, increases by roughly 5% per 100 rem of exposure. So, after 10 years on Mars, your cancer risk has increased from 40% to about 65%. After 20 years to about 90%, you're almost certain to develop cancer if you live on Mars for 2 decades. It might be treatable, Mars will have medical facilities, and cancer treatment has improved greatly. But you're still looking at surgery, chemotherapy, radiation therapy, all the unpleasantness of cancer treatment. And some cancers aren't very treatable. Lung cancer, brain cancer, pancreatic cancer, these still have poor survival rates, even with treatment. Radiation also affects fertility directly. The cells that produce eggs and sperm are particularly sensitive to radiation damage. Women are born with all the eggs they'll ever have, approximately 1 to 2 million at birth, declining to about 300,000 by puberty. Radiation damages these eggs over time. Every year on Mars, more eggs accumulate DNA mutations. By the time a woman in her 30s tries to conceive, a significant fraction of her eggs may have chromosomal abnormalities that lead to miscarriage or birth defects. Men continuously produce new sperm from stem cells called spermatogonia. That sounds better, fresh sperm not accumulating damage over decades. But the spermatogonia themselves accumulate radiation damage over time. As these stem cells divide to produce sperm, they can pass mutations into the sperm DNA. Studies of radiation workers on Earth, such as nuclear plant workers and radiologists, show increased rates of genetic abnormalities in offspring when fathers have high cumulative radiation exposure. There's also concern about transgenerational effects, radiation damage that affects not just the exposed individual but their children and grandchildren. If radiation causes mutations in eggs or sperm DNA, those mutations get passed to the next generation. If those mutations occur in genes involved in DNA repair or cell division control, the next generation might have reduced ability to repair their own radiation damage, leading to accelerated damage accumulation. Over multiple generations, this could compound. Research on this is limited because it requires multi-generational studies, which are difficult with humans. Animal studies show mixed results. Some studies show transgenerational effects. Children and grandchildren of irradiated mice show increased cancer rates and reduced lifespan, even though they themselves weren't directly exposed. Other studies show resilience populations adapting to chronic low-level radiation. The Chernobyl exclusion zone surprisingly has thriving wildlife populations despite elevated radiation levels. Some species appear to have evolved enhanced DNA repair mechanisms in just 40 years, about 20 generations for mice and birds. Could humans do the same? Maybe. Evolution works on populations under selection pressure. Mars colonists would be under intense selection pressure for radiation resistance. People whose DNA repair mechanisms work better, whose immune systems clear damaged cells more effectively, whose reproductive cells maintain integrity despite radiation, those people would have more surviving children. Over many generations, Mars humans might evolve significant radiation resistance. But evolution is slow compared to radiation damage. It takes generations for beneficial mutations to spread through a population. Radiation damage happens to every individual every day. The race between evolutionary adaptation and accumulated damage might not favor the colonists. By the time significant radiation resistance evolves, maybe generation 50 or 100, the population might already be suffering from high rates of cancer, infertility, and genetic disorders that make long-term survival questionable. This is the radiation trap. Mars has no magnetic field and never will. We can't give Mars a magnetic field with any technology we can realistically imagine. Some scientists have proposed placing a giant magnetic shield at the Mars-Sun L1 Lagrange point, a location in space between Mars and the Sun where gravitational forces balance. This shield would generate an artificial magnetic field that deflects solar wind around Mars, potentially allowing Mars's atmosphere to thicken over time as it's no longer stripped away by solar wind. The idea was published by NASA scientists in 2017, but the engineering challenges are staggering. A structure kilometers across, generating a powerful magnetic field continuously for centuries, held at a gravitationally unstable point requiring constant course corrections. It's theoretically possible, but practically far beyond our current capabilities. So radiation is simply a fact of life on Mars. Every colonist accepts it. You live with it, you manage it through shielding and limiting exposure time, you accept the health consequences. You get screened for cancer regularly. You bank eggs or sperm before exposure accumulates too much. You make choices about how many years you're willing to spend on Mars before the cancer risk becomes unacceptable. And you hope that over 800 generations, human biology adapts faster than radiation damage accumulates. Because if it doesn't, if cumulative damage outpaces evolutionary adaptation, then Mars colonies will face declining health, declining fertility, and declining lifespan each generation. The colony might not die in a catastrophe. It might just fade out slowly, each generation slightly less viable than the last, until the last Mars-born human dies without descendants. This is what 20,000 years under constant radiation exposure means. It's not a problem you solve. It's a pressure you endure, and hope evolution saves you before the damage becomes irreversible. Gravity breaks your bones slowly. Radiation unravels your DNA quietly. And those are just the biological threats. There's also the question of whether colonies can survive economically and logistically, because here's a truth that shatters the romantic vision of Mars homesteads: no colony will ever be truly self-sufficient. Right now, the International Space Station recycles 93% of its water through a complex system that captures humidity from the air, processes urine through filtration and distillation, and makes it drinkable again. That sounds impressive until you realize they still need regular resupply missions from Earth. Every few months, a cargo spacecraft arrives, carrying the 7% they can't recycle, plus food, spare parts, equipment, and experiments. The ISS is in low Earth orbit just 400 kilometers up. Supply ships can reach it in hours from launch. Mars is a different scale entirely. At its closest approach to Earth, an alignment that happens every 26 months, Mars is 55 million kilometers away. Travel time is 6 to 9 months, depending on trajectory and propulsion technology. At its farthest, when Mars and Earth are on opposite sides of the Sun, the distance exceeds 400 million kilometers. During these periods, travel is prohibitively expensive in fuel and time. Supply missions can only launch during favorable alignments every 26 months. Miss that window because the spacecraft isn't ready, because the rocket fails, because funding doesn't come through, and you wait more than 2 years for the next opportunity. This creates a fundamental vulnerability. Imagine a Mars colony with 5,000 people has carefully calculated their supply needs. They have 18 months of food in storage. They expect a supply ship in 9 months. Then word arrives from Earth: the spacecraft failed during launch. Catastrophic engine failure. The ship is destroyed. Next launch window is 26 months away. The colony has 18 months of food. What happens? Immediate crisis mode. Rationing begins that day. Every meal is reduced by 20%. Greenhouse production is pushed to maximum. Farmers work longer hours, plant every available space, try to accelerate growth cycles. But greenhouses have limits. You can't simply produce more food by wanting it. Plants need time to grow, need nutrients from soil that might already be depleted. By month 15, the first deaths occur: elderly colonists, people with health conditions, anyone whose body can't handle the malnutrition. By month 18, when the stored food runs out completely, the colony is surviving on greenhouse production alone, which was never designed to feed everyone. 20% of the population dies before the next supply ship arrives 2 years later. The survivors are traumatized, malnourished, and they've learned that dependence on Earth is a vulnerability that can kill them. This isn't hypothetical disaster planning. This is orbital mechanics and logistics. On Earth, when supply chains broke during the COVID pandemic in 2020, people experienced shortages of toilet paper and certain foods for weeks or months. Inconvenient, yes, but not lethal. Now imagine those delays measured in years, and the shortage is medicine, or food, or critical equipment components. A supply chain break on Mars isn't an inconvenience. It's existential. NASA's own studies estimate that a Mars colony would require 200 to 1,000 years to reach 80 to 90% self-sufficiency. Not 100%, 80 to 90. They'd still need Earth for specialized manufacturing. Computer chips require ultra-clean fabrication facilities. Certain medicines need complex pharmaceutical manufacturing. Advanced medical equipment can't be built without industrial infrastructure that takes decades to establish. And genetic diversity requires new people arriving periodically. Even with 10,000 colonists, the estimated minimum viable population to avoid inbreeding genetic diversity slowly erodes without fresh DNA from Earth. The vision of self-sufficient Mars homesteads is marketing, not reality. What actually emerges is interdependence across the solar system. Mars grows food in greenhouses because they have the advantage of soil and some gravity. Asteroid mining operations extract metals from the belt because mining in zero gravity is easier than fighting gravity wells. Europa provides water ice from its surface. Earth sends advanced technology and trains specialists. Each node depends on others for things it cannot produce locally. Biosphere 2. An Earth-based experiment from the 1990s demonstrated how hard closed-loop life support really is. 8 people sealed inside a 3-acre facility with crop areas, a ocean, forest, and savanna biomes. The goal was complete self-sufficiency, recycling everything, growing all food, maintaining atmospheric balance. It failed within 2 years. Oxygen levels dropped dangerously because soil microbes respired more than plants could replenish. Crops failed due to pests and pollination problems. The crew began fighting over food rations. And this was on Earth, where they could open the door and leave if things went catastrophically wrong. Earth's ecosystems took billions of years to balance into stable cycles involving thousands of species in complex food webs. An artificial habitat has dozens of species at most. It's fragile. One pest outbreak destroys crops. One equipment failure stops air recycling. One contamination event poisons the water supply. There's no redundancy in small systems. Everything depends on everything else, and one failure cascades into others. Over 20,000 years, supply chains will break repeatedly. Political systems will collapse. Wars might happen, not Star Wars space battles, but blockades and embargoes. One colony withholding critical resources to gain leverage over another. Economic systems will boom and crash. Technologies will advance, but also become obsolete, requiring complete retooling. Colonies will fail, wiped out by plagues, equipment failures, environmental disasters, social collapse. Each time a colony fails, the network has to adapt. Other colonies need to find new sources for whatever that failed colony provided. Trade routes have to be rerouted. Sometimes the network successfully reorganizes. Sometimes a cascade failure spreads with multiple colonies collapsing as their dependencies break. The system survives only if it maintains more connections than breaks, more cooperation than conflict, more resilience than fragility. True independence is impossible, but interdependence can work if, and only if, humanity maintains the web of connections across vast distances and long-time delays. If colonies keep trading, keep communicating, keep cooperating instead of isolating or fighting, if supply ships keep flying despite the expense and risk, if Earth keeps supporting colonies even when the economic return isn't immediate, if colonies support each other during crises instead of exploiting vulnerabilities, 20,000 years means 20,000 years of maintaining that web, repairing it when it breaks, expanding it as new colonies form, strengthening it against internal conflicts and external pressures. Success isn't measured by how many colonies we establish, but by how well we maintain the connections between them. Because in space, connection is survival, and isolation is death. And then there's Mars itself, which isn't just indifferent to human life. It's actively hostile in ways that never stop, never relent, never give you a moment of peace. Martian dust is fundamentally different from Earth dust. It's incredibly fine particle sizes, averaging 3 micrometers, about 1/30th the width of a human hair. That's fine enough to get into anything. It penetrates seals. It works its way into bearings and hinges. It gets tracked into habitats despite airlocks and cleaning protocols. And once inside, it's everywhere in the air you breathe, on every surface, in every crevice. But it's worse than just being fine. Martian dust is electrostatically charged from friction and ultraviolet radiation. It clings to surfaces like it's attracted magnetically. Astronauts on Apollo missions dealt with lunar dust that had similar properties, and they reported that it stuck to everything, spacesuits, equipment, even floating in the cabin despite their best efforts to keep it out. One astronaut, Harrison Schmitt, on Apollo 17, developed an allergic reaction to lunar dust hay fever symptoms that appeared whenever he was exposed. Martian dust would be similar but worse, because you'd be exposed to it for years, not just a few days. And it's toxic. Martian dust contains perchlorates chlorine compounds that are harmful to human health. Perchlorates interfere with thyroid function, affecting metabolism and hormone regulation. They can cause developmental problems if pregnant women are exposed. Long-term exposure leads to respiratory problems as the particles accumulate in lungs. Studies by the Phoenix Lander in 2008 found perchlorate concentrations in Martian soil of 0.4 to 0.6% by weight. That's high enough to cause serious health problems with chronic exposure. You can't fully filter perchlorates out because they're chemically bound in the dust particles. You can reduce exposure with good habitat air filtration, with strict protocols for cleaning spacesuits before entering living areas, with minimizing time spent outside. But you can't eliminate it. Every EVA brings some dust inside. Every breath includes trace amounts. Over years, it accumulates in your body. Then there are the dust storms. Mars has regional dust storms, frequently hundreds per Martian year. But every few Martian years, roughly once per 3 Earth years, conditions align to produce a global dust storm that engulfs the entire planet. These storms can last for months. The dust becomes so thick, it blocks 99% of sunlight. The sky turns completely opaque. Temperatures drop as solar energy can't reach the surface. In 2018, a global dust storm killed the Opportunity rover. The rover was solar-powered. When the storm blocked the sun, its batteries drained. The rover went into hibernation mode to preserve power, waiting for the storm to clear. It never woke up. When the storm finally cleared, months later, the rover's batteries had degraded beyond recovery in the cold, and it couldn't reboot. NASA tried for months to re-establish contact. Opportunity never responded. A rover that had operated for 15 years died because of one dust storm. Now imagine you're a Mars colony depending primarily on solar power. A global dust storm hits. Sunlight drops to near zero. Your solar panels stop generating power. You switch to battery reserves, but batteries drain fast when you're running life support for thousands of people. You start rationing power immediately. Non-essential systems shut down. Heating is reduced to minimum levels. People huddle in insulated sleeping areas wearing every layer of clothing they own. The storm was forecast to last 3 months based on historical patterns. It's been 4 months, 5 months, 6 months. Your battery reserves are critical. You're discussing which systems to shut down next. Life support can't be compromised, but what about food production? If you shut down greenhouse climate control, crops die, and it takes months to recover food production after the storm. Do you sacrifice future food security for current power needs? These are the decisions Mars colonists face during major dust storms. When the storm finally clears after 8 months, you've survived, but the colony has suffered. Solar panels are coated in dust, reducing their efficiency by 30% until they can be cleaned, a labor-intensive process requiring EVA crews. Equipment has failed from cold temperatures during the power rationing. Seals have cracked from thermal cycling. Greenhouses lost some crop varieties that couldn't survive the reduced heating. And some colonists, the very young, the very old people with health vulnerabilities, didn't make it through the 8 months of cold and stress. The temperature swings on Mars are brutal and constant. Mars averages -80 degrees Celsius colder than the coldest temperature ever recorded in Antarctica. But at the equator, during summer, surface temperatures in direct sunlight can reach +20 degrees Celsius. That's a 100 degrees Celsius swing between night and day, between winter and summer. Materials expand when heated, contract when cooled. Do this repeatedly, thousands of times over years, and materials fail. Seals crack, joints loosen, metal fatigues. Nothing lasts as long as it should, because everything is constantly being thermally stressed. And the atmosphere, calling it an atmosphere, is generous. Mars's atmospheric pressure at the surface is 0.6% of Earth's pressure. That's essentially vacuum. 95% of that thin atmosphere is carbon dioxide. Step outside without a spacesuit, and you'd have about 15 seconds of consciousness before passing out from lack of oxygen. Death would follow within 2 minutes, not primarily from cold, but from the low pressure causing your blood to boil at body temperature. Living on Mars means living in a hostile environment that never becomes friendly, never offers a moment of safety outside your pressurized habitat. Every breath requires a functioning life support system. Every step outside requires a full spacesuit with redundant systems. Every day is maintenance day, because the environment is constantly trying to break your equipment. A cracked seal, a clogged filter, a frozen valve, any one of these small failures means someone dies. Over 800 generations, Mars doesn't get easier. You don't terraform it. That requires technology and timescales beyond what we can achieve. The colonists just get better at surviving it. They develop better materials that resist thermal cycling. They design better dust filtration systems. They learn to predict storms better and prepare for them. But Mars itself never changes. It remains deadly, hostile, unforgiving. And surviving there for 20,000 years means accepting that every single day the environment is trying to kill you, and your survival depends on technology and vigilance that can never lapse. While you're enduring the physical hostility, there's another kind of isolation that erodes the human spirit, the emotional kind imposed by light-speed delay that makes real connection impossible. Mars, at its closest approach to Earth, is 3 light minutes away. That means a radio signal takes 3 minutes to travel from Mars to Earth. At its farthest, Mars is 22 light minutes away. On average, taking into account the full orbital cycle, Mars is about 12.5 light minutes from Earth. Send a message, wait 12.5 minutes for it to arrive. They respond immediately, and their response takes 12.5 minutes to get back. Total time for a question and answer, 25 minutes. You can't have a conversation. You can't call home and talk to your family in real time. Every interaction is asynchronous, like writing letters or emails, except you're waiting 25 minutes per exchange instead of hours or days. The spontaneity of human communication dies. You can't share a joke and hear immediate laughter. You can't get comfort in real time when you're hurting. Every emotional exchange is delayed, displaced in time, stripped of the immediacy that makes connection feel real. Imagine your parent on Earth is dying. You get a message that they're in the hospital. Prognosis is poor, it might be hours. You record a message pouring your heart out, telling them you love them, sharing memories, saying everything you need to say. You hit send. Your message travels for 12.5 minutes across space. Your parent receives it, but by the time they do, they might already be unconscious. Or worse, already gone. They respond, or someone responds for them, and that response travels 12.5 minutes back to you. You receive it 25 minutes after you sent your message. Your parent has been dead for 20 minutes, and you're just now getting their last words. You're grieving on a time delay. The moment of connection you desperately needed happened in 2 different time frames, separated by the fundamental speed limit of the universe. This is what communication looks like across interplanetary distances. Every important conversation happens like this, displaced, delayed, disconnected from the immediate emotional moment. Psychological studies of isolated populations provide some insight into what this does to people. Antarctic winter-over crews spend months at research stations with limited communication to the outside world. Submarine crews on long deployments experience communication restrictions. These studies consistently show that communication delays and restrictions increase feelings of isolation, make conflict resolution harder, and erode the sense of connection to home. When you can't communicate naturally, relationships suffer. People feel abandoned even though rationally they know the delay isn't anyone's fault. For Mars colonists, this psychological burden is permanent. It's not a temporary deployment, it's their life. They wake up every day knowing that everyone they care about on Earth is 25 minutes away in communication time. Quick check-ins are impossible. Spontaneous conversations don't exist. The emotional texture of relationships changes fundamentally. You can't maintain the same kind of closeness when every interaction is delayed and requires conscious effort to compose messages. After 5 to 10 generations, 125 to 250 years, something shifts. No one alive remembers Earth firsthand. It exists only in stories, videos, photos, databases. The cultural references diverge. Earth children grow up consuming Earth media, dealing with Earth problems, thinking about Earth futures. Mars children grow up with Martian concerns, dust storms, radiation levels, greenhouse yields, equipment maintenance. The shared context that enables meaningful communication erodes. Mars colonists start communicating with Earth less frequently. At first, weekly messages become monthly, then quarterly, then only on special occasions, holidays, births, deaths. Not because anyone stops caring, but because maintaining relationships across such vast gulfs of time and experience takes enormous effort for diminishing emotional return. They write to Earth relatives the way you might write to distant cousins you met once at a family reunion, acknowledging the connection but not feeling it deeply. Earth stops being home in any meaningful sense. It becomes where humans originated the way Africa is, where Homo sapiens originated, but most people don't feel a personal connection to East African Rift Valley just because ancestors lived there 200,000 years ago. Mars colonists develop their own culture, their own identity, their own sense of home, and that home is Mars, not Earth. Earth is just another planet where other humans happen to live. The speed of light doesn't just limit travel. It limits love, limits connection, limits the sense of belonging to something larger than your immediate colony. You can intellectually know that billions of humans live on Earth, but you can't feel connected to them when communication is asynchronous and takes 25 minutes per exchange. The psychological reality of 25-minute delays is isolation. Over 20,000 years, this isolation compounds. Colonies don't just drift apart physically as they spread across the solar system. They drift apart culturally, emotionally, psychologically. Each colony develops its own dialect, its own customs, its own values shaped by local conditions. Mars culture diverges from Earth culture. Titan culture diverges from both. The asteroids develop their own identity. 800 generations later, humans across the solar system might still share DNA and evolutionary history, but they're not one culture anymore. They're dozens of separate cultures connected tenuously by trade and occasional messages, but not by any shared sense of common identity. And this isn't something technology can fix. We can't send messages faster than light. That's prohibited by physics as we understand it. We can't overcome the communication lag. We can only accept it and adapt to it, which means accepting that expansion across the solar system means fragmentation of human culture into multiple separate cultures, each isolated by light-speed delays that make real emotional connection impossible across the, say, distances. This is what 20,000 years of communication lag means. Not technological limitation, but fundamental psychological isolation. The human species becoming not one family separated by distance, but many families who barely know each other, connected only by dim memories of a common origin that gets more mythological with each passing generation. And this leads to something even stranger, the transformation of Earth from lived reality to abstract history to pure mythology across just a few hundred years. Generation 1 arrives on Mars from Earth. They remember Earth, viscerally blue skies, the smell of rain on pavement, the feeling of wind in their hair, the taste of fresh strawberries grown in actual sunlight. Earth is real to them. It's home, even though they've chosen to leave it. They tell their children about Earth, constantly wanting to pass on the memory of where humanity came from. Generation 2 children, born on Mars to Generation 1, parents grow up hearing these stories. They see videos and photos of Earth. They know intellectually that Earth exists and what it's like. But they've never experienced it. They've never felt rain, never seen a cloud, never walked through a forest. Earth is abstract to them. It's the place my parents came from, but it's not their home. Their home is Mars' red dirt dust storms, pressurized habitats. That's what's real. Generation 5 great-great-grandchildren of the original colonists hear stories about Earth from their grandparents, who heard them from their grandparents. The stories have been filtered through multiple retellings. Details change. Exaggerations creep in. Earth starts to sound almost magical, a place where you could walk outside without a spacesuit, where water fell from the sky, where plants grew everywhere without greenhouses. Is it real or embellished? They're not sure. Generation 10, about 250 years after colonization, consists of people whose most recent Earth-born ancestor was their great-great-great-great-great-grandparents. That's 8 generations removed. No one alive has met anyone who lived on Earth. Earth exists in databases and carefully preserved videos, but those feel like history documentaries about ancient Rome or Egypt. Important historically but not personally relevant. Generation 15, about 375 years after colonization, faces an identity crisis. Some educators try to maintain Earth culture, teaching Earth history, showing Earth videos, preserving Earth languages and customs, but it feels increasingly artificial. They're trying to maintain connection to a place that's 25 light minutes away in communication time that no one has visited in centuries, that exists only as data and stories. The students learn it the way you might learn about ancient Babylon, intellectually interesting but emotionally distant. Other educators argue for letting Martian culture develop naturally. Yes, humans came from Earth originally, but that was 400 years ago. Martians are their own people, now with their own identity, their own challenges, their own future. Trying to maintain Earth culture is living in the past. Better to acknowledge Earth as ancestral homeland, but focus on building Martian identity going forward. This debate happens in every colony across the solar system as they age. How much do you preserve from Earth? How much do you let local culture evolve? There's no right answer, and different colonies make different choices. Some become very Earth traditional, almost obsessively maintaining Earth customs. Others embrace local identity, fully treating Earth as interesting history but not their culture. Cultural anthropologists who've studied oral traditions across Earth cultures have found that without writing or strong institutional preservation, oral traditions significantly drift after 7 to 10 generations. Stories change, details are forgotten or altered. Sometimes entirely new elements are added. The story that Generation 15 tells about Earth is substantially different from the story Generation 1 told, even though they're trying to preserve the same memory. And on Mars, they don't have the physical anchors that help preserve cultural memory on Earth. On Earth, you can visit the place where your ancestors lived. You can see the landscape they saw, touch the buildings they built, walk the paths they walked. Physical places anchor memory. They make history tangible. But on Mars, there are no ancient places, just habitats built in the last few centuries. No landmarks existed before humans arrived. There's no sacred mountain, no ancestral river, no ancient tree under which important events occurred. Just metal habitats and red dust. Without physical anchors, memory fades faster. Generation 20 says, Earth is the blue planet in the old stories, and they mean it literally. It's become mythology, no more real to them than Atlantis or El Dorado is to us. They intellectually know Earth exists, and humans live there, but emotionally, it's not real. It's a story. A beautiful story, yes, the planet with breathable air and oceans and forests. But a story nonetheless, not a place they feel connected to. By Generation 50, about 1,250 years after colonization, Earth is purely mythological. It's the Genesis place where humans were created by evolution before they spread to the stars. Religious or quasi-religious conceptions of Earth develop. Some Martians speak of Earth with reverence as a sacred origin place they hope to someday visit even though they never will. Others treat Earth dismissively as a place humans had to leave because they'd outgrown it. Earth becomes whatever people need it to be, psychologically proof that humans came from paradise, or proof that humans are meant to explore, or warning about environmental destruction, or promise of abundance. Earth stops being a real place and becomes a symbol onto which different meanings are projected. Over 20,000 years, this pattern repeats across all colonies. Each colony develops its own origin story incorporating Earth, but the story diverges from historical reality. Mars colonists remember Earth one way, Titan colonists another, asteroid communities another. By Generation 800, if you gathered humans from across the solar system and asked them to describe Earth, you'd get dozens of different descriptions, all supposedly based on the same ancestral memory. All different, because memory is malleable and myths evolve, and none of them can visit Earth to check if their memories are accurate. The humans who evolved on Earth now live scattered across dozens of colonies, each colony too adapted to its local gravity and environment to return to Earth without dying. So, Earth remains forever mythological, the origin place that no one can visit, that everyone imagines differently, that unites humans conceptually but divides them practically because everyone's version is different. This is what 20,000 years does to cultural memory. It doesn't preserve, it transforms. And the transformations are unpredictable, shaped by local needs and accidents of cultural transmission. Until the original truth is buried under layers of accumulated mythology, and no one can dig down to bedrock anymore. If cultural memory fades and diversifies, genetics undergo an even more fundamental transformation. Because 20,000 years of isolation in different gravity wells with different selection pressures means one thing: speciation. Evolution never stops. It doesn't pause because we have technology or because we think of ourselves as beyond biology. Evolution is simply the change in allele frequencies in populations over time, driven by mutation, selection, and genetic drift. Humans on Mars will evolve differently from humans on Earth, and both will evolve differently from humans on Titan or in asteroid habitats. After 800 generations, these populations won't just be culturally distinct, they'll be genetically distinct, potentially to the point of being separate species. Start with population genetics basics. The original Mars colony might have 1,000 to 5,000 people. That's a small population compared to billions on Earth, which means genetic drift happens faster. Genetic drift is random change in allele frequencies due to sampling effects. In small populations, random events have outsized effects. If a few people carrying certain genes happen to have more children, those genes become more common in the next generation, not because they're better adapted, but because of chance. Then add selection pressure. On Mars, people who happen to have genes for denser bones in low gravity do better. They have fewer fractures, less pain, better mobility. People whose DNA repair mechanisms are more efficient handle radiation better, they get cancer, less often live longer, have healthier children. People whose circadian rhythms are more flexible adapt better to Mars's 687-day year. These traits get selected for. Over generations, Mars humans become shorter-lived due to radiation, taller due to low gravity, and physiologically different in dozens of small ways. Within 10 generations, about 250 years, doctors noticed children born on Mars showing consistent differences from Earth humans. These differences aren't abnormalities, they're adaptations. Thicker eyelid tissue provides some protection against radiation. Denser lung tissue compensates for lower atmospheric pressure. Longer bones grow in response to low gravity. These traits cluster together because they're being selected for simultaneously. By generation 51,250 years, Martian humans and Earth humans look visibly different. Martians average 10 to 15 centimeters taller due to reduced gravity, allowing longer bone growth. Their slimmer lower gravity doesn't favor heavy muscle mass. Their faces are slightly different fluid distribution in low gravity during development shapes facial bones differently. They move differently, their gait and posture are adapted to 0.38 g. By generation 205,000 years, the genetic differences are substantial enough that population geneticists studying them would debate whether to classify Martian humans as a subspecies. They can still interbreed with Earth humans and produce fertile offspring, but the offspring often have health problems. Their physiology is a mismatch between two different gravitational adaptations. A half-Earth, half-Mars child born on Mars might have bones too heavy for Martian gravity, making movement difficult. The same child born on Earth might have bones too light for Earth gravity, making fractures likely. By generation 820,000 years, Mars humans and Earth humans are reproductively isolated, not by genetics alone, but by physics. Even if a Mars human and Earth human could meet and wanted to have children, where would the pregnancy happen? On Mars, the Earth human parent can't stay long-term without bone loss, making return impossible. On Earth, the Mars human parent literally can't survive the gravity. The pregnancy has to happen somewhere, and that somewhere determines whether the fetus can develop properly. If the parent's physiologies are too different, the fetus might not develop properly anywhere. This is speciation in action, not the slow million-year process of Homo sapiens diverging from earlier hominins, but rapid speciation accelerated by small population sizes, strong selection pressures, and complete reproductive isolation between populations. It's similar to how island populations rapidly diverge from mainland populations. Darwin's finches on the Galapagos speciated in thousands of years, not millions. And it's not just Mars. Every colony evolves separately. Titan colonists living in 0.14 G and -180-degree temperatures adapt to those conditions. Asteroid colonists living in effectively 0 G adapt to that. Colonists near Jupiter adapt to intense radiation. Each colony becomes a separate breeding population under different selection pressures, diverging genetically from all others. After 20,000 years, you don't have one human species spread across the solar system. You have maybe 10 to 20 distinct subspecies, and some might have diverged enough to be considered separate species. Homo sapiens on Earth, Homo martianus on Mars, Homo titanus on Titan, Homo asteroid in the belt, each carrying human DNA, each descended from the same ancestral population that left Earth, each now adapted to their local environment and unable to interbreed successfully with others. Some might argue this is failure. We set out to spread humanity across the solar system, and instead we fragmented into multiple species. But from an evolutionary biology perspective, this is success. This is adaptation. This is life doing what life does, diversifying to fill available niches. We're not less human for adapting. We're more successful as a lineage because we've diversified into multiple branches that can survive in different environments. But it does mean the end of humanity as one species with one identity. It would feel like a meeting of related but distinct species, like if Homo sapiens, Neanderthals, and Denisovans all still existed and held a conference. Related, yes. Sharing common ancestry, yes. But different species, with different biologies, different capabilities, different futures. The solar system becomes home not to humanity, but to the human family. Multiple species descended from one origin, now radiating outward into different adaptive zones, following evolution's imperative to diversify and adapt. This raises the most sobering question: can any chain of 800 generations hold without breaking? The mathematics are brutal. Imagine a relay race with 800 runners. Each runner carries the baton for one generation, 25 years, then passes it to the next. If each runner has a 99% success rate, just a 1% chance of dropping the baton, what are the odds? All 800 succeed. It's 0.99 to the 800th power. Calculate that and you get 0.0003. That's 0.03% chance of success. 99.97% chance that somewhere along that chain, someone drops the baton and everything ends. That's the statistical reality of 20,000 years. It's not about one generation succeeding spectacularly. It's about 800 generations not failing. 800 consecutive passes of the baton, each one executed successfully, despite enormous pressures and countless failure modes. And the failure modes multiply at every level. Technical failures, life support systems break habitats, breach equipment wears out faster than it can be replaced. Biological failures, plagues sweep through colonies, crop diseases, destroy food supplies. Fertility rates decline due to accumulated genetic damage. Social failures, wars break out over resources, governments collapse, cultural cohesion fractures as different factions pursue incompatible visions. Environmental failures, larger than expected dust storms, solar flares, small asteroid impacts hitting colonies. Systemic failures, supply chains break, trade networks collapse, colonies become isolated and unable to sustain themselves. Historical precedent is not encouraging. Approximately 90% of human civilizations that have ever existed have collapsed within 1,000 years. The Maya at their peak had millions of people across hundreds of cities, advanced mathematics and astronomy, sophisticated agriculture, collapsed within centuries. Easter Island had a thriving culture that built the famous Moai statues, collapsed possibly due to deforestation and resource depletion. The ancestral Puebloans built complex cliff dwellings and irrigation systems, abandoned them within a few hundred years, likely due to drought. And these civilizations collapsed with Earth's entire biosphere as a safety net. If the crops failed in one region, people could migrate to another. If one settlement collapsed, others survived. Earth is fundamentally habitable, 14.7 psi of breathable atmosphere, liquid water in rivers and lakes, wild plants and animals that could be harvested in emergencies. Mars has none of that. If a Mars colony fails, there's nowhere to migrate to. There's no wilderness to retreat into and live off the land. There's only other colonies, and they have their own problems. The terrifying fragility is that it only takes one generation failing to pass the baton successfully. One generation that doesn't maintain the equipment properly, and systems degrade beyond repair. One generation that starts a war over ideology or resources, fracturing the colony into competing factions. One generation that loses the sense of purpose, forgets why they're doing this, why it matters, and maintenance standards, slip safety protocols are ignored. The slow accumulation of small failures that leads to catastrophic collapse. Or one generation faces a crisis they can't overcome. A plague that kills 40% of the population, dropping below the minimum viable population for genetic diversity. A cascade failure where multiple systems break simultaneously and they don't have enough trained people to fix everything fast enough. A political revolution that replaces functional governance with dysfunction. A major solar flare that fries electronics faster than they can be replaced. Think of it as a Jenga tower, 800 blocks high. Each generation removes one block the challenges they face and places it on top the solutions they create and burdens they pass forward. The tower starts stable but becomes increasingly precarious. Early generations have it easier. Systems are new, supplies are plentiful, purpose is clear. Later generations inherit an aging infrastructure, depleted resources, and accumulated problems. By generation 400, the tower is swaying. By generation 600, any wrong move could topple it. By generation 800, that it's still standing is a statistical miracle. Statistical reality says extinction is nearly certain somewhere along that chain. Survival of all 800 generations would be extraordinary, requiring not just good technology or good planning, but cultural continuity that maintains purpose and competence across timescales. Longer than any civilization has ever achieved. It requires 800 generations of people choosing every single day to do the maintenance, make the sacrifices, preserve the systems, pass forward what they inherited, intact or improved. Success isn't about brilliance. It's about reliability, consistency, patience, and the refusal to be the generation that breaks the chain. It's about ordinary people doing unglamorous work, checking seals, maintaining filters, growing food, teaching children for their entire lives, knowing they're one link in a chain of 800, and if they fail, everyone after them fails too. That's an enormous psychological weight. It's also the only way 20,000 years works, which is why 20,000 years isn't fundamentally about technology. It's about creating a culture that thinks in millennium-scale time, values continuity over innovation, and measures success in lineages rather than lifetimes. On Earth, some cultures achieved this. Aboriginal Australians lived in the same regions for approximately 65,000 years, the longest continuous culture in human history. They maintained knowledge of waterholes, seasonal patterns, and navigation routes through oral traditions passed down across thousands of generations. They thought in deep time naturally because their survival depended on it. Indigenous peoples across the Americas maintained societies for 15,000 years. The Iroquois Confederacy had a governing principle called the seventh generation principle. Decisions should consider the impact on descendants 7 generations into the future. That's about 175 years ahead. Not quarterly earnings, not election cycles, but impacts on people not yet born. Polynesian navigators crossed the Pacific Ocean for over 3,000 years using oral navigation traditions. They passed knowledge of stars, wave patterns, and bird migration through songs and apprenticeship. No written records, just cultural transmission generation after generation, because losing that knowledge meant death at sea. These cultures understood something modern, industrial society has forgotten. Long-term survival requires thinking far beyond your own lifetime. You make decisions not for your benefit, but for your grandchildren's grandchildren. You maintain knowledge not because it's immediately useful, but because someday it will be essential. You preserve traditions not out of nostalgia, but because traditions encode survival wisdom accumulated over centuries. Modern industrial society does the opposite. We optimize for quarterly profits, 3-month timescales. Political systems operate on election cycles 2 to 6 years. Corporate strategy plans 5 to 10 years ahead at most. Even very long-term planning infrastructure projects, climate policy rarely extends beyond 50 years. We barely think beyond our own generation and almost never think beyond our grandchildren's generation. Space colonization requires reversing that completely. Colony planners have to think in terms of centuries and millennia. Will this decision help generation 100, generation 500, generation 800? Not will this maximize profit next quarter, but will this system still function in 3,000 years when our descendants rely on it? This requires fundamentally different values. Patience over speed, maintenance over innovation, reliability over efficiency, teaching over achieving. These values sound boring compared to move fast and break things startup culture or maximize shareholder value capitalism, but they're what actually enables survival across deep time. It means treating culture as infrastructure. Stories, rituals, traditions aren't just entertainment or nostalgia. They're the mechanism for transmitting purpose across generations. You tell stories about why the colony exists, what values matter, what mistakes to avoid. You create rituals around maintenance tasks, so they're not just boring chores but meaningful practices connecting you to past and future generations. You establish traditions that keep the mission central to cultural identity, so even generation 500 remembers why they're doing this. It means no single generation owns the colony. You're stewards. You inherited systems from the previous generation. Your job is to maintain them, improve them if possible, and pass them to the next generation in at least as good condition as you received them. Preferably better, but never worse. Breaking something and leaving it for the next generation to fix is betrayal of the highest order. It means evaluating decisions by their long-term consequences. Before implementing a new technology, ask, can we maintain this for 300 years? Do we have the knowledge base to repair it? Can we manufacture spare parts locally? If the answer is no, maybe stick with simpler technology. That's less impressive but more maintainable. A solar panel that lasts 50 years and can be repaired with local resources is better than a fusion reactor that lasts 200 years but requires specialty parts from Earth. Indigenous Australians preserved songlines, maps encoded in songs for 65,000 years without writing. The songs described the landscape told where water could be found, explained seasonal patterns, encoded law and custom. Lose the songs and you lose survival knowledge. So, the songs were taught carefully, generation after generation, with enormous cultural importance placed on accuracy. That's the mindset space colonists need, not for songs, but for the technical and cultural knowledge that keeps everyone alive. 20,000 years means learning to be indigenous to vacuum, learning to measure time in generations, not quarters, learning to value the chain of continuity more than individual achievement, learning that your purpose is to be a good ancestor, not a celebrated hero. The colonists who succeed will be those who adopt this mindset. The colonists who fail will be those who stay focused on short-term metrics and lose sight of the deep time mission. Culture is the real technology. Life support keeps you alive today. Culture keeps the colony alive for 800 generations. But even with the right culture, even with deep time thinking, there's a humbling truth: we still don't know if any of this is possible. Can humans reproduce in low gravity? Unknown. We have concerning mouse data, but mice aren't humans, and we can't ethically test human pregnancy in space until we try it. Will radiation damage accumulate faster than evolution can compensate? Unknown. We can model it, but models aren't reality. Will closed-loop life support systems function reliably for centuries? Unknown. The longest we've tested is 2 years on Earth, with emergency exits available. Will colonists maintain psychological health across centuries of isolation? Unknown. Antarctic stations and submarine studies give hints, but those are temporary deployments, not permanent settlements. Can cultures maintain purpose and cohesion across 50 generations? No precedent exists. The longest continuous culture is Aboriginal Australian at 65,000 years, but they lived on a habitable planet with room to migrate when conditions changed. Mars colonists live in metal boxes where migration isn't an option, and any cultural collapse means death. Our entire Mars colonization strategy is educated guesswork. Based on 60 years of space experience, the ISS, Apollo missions, robotic probes, satellite data, the longest any human has stayed in space is 437 days. Valery Polyakov on Mir Space Station 1994-95 returned with significant bone loss and muscle atrophy, took months to fully recover. We're extrapolating from 437 days to 20,000 years. That's extrapolating by a factor of 16,000. Total humans who've been to space as of 2024, approximately 600 people. Total cumulative time humans have spent in space, roughly 150 person years. We're taking 150 person years of experience and trying to predict what happens over 200 million person years for a 10,000 person colony over 20,000 years. We're scaling up by 7 orders of magnitude. Imagine if early aviation pioneers, having accumulated 150 hours of total flight experience in 1903, tried to predict what aviation would look like in the year 22,000. They'd be wildly wrong about almost everything. We're in that same position with space colonization. We know just enough to know it's possible in principle, but not nearly enough to predict what actually happens at scale over deep time. Scientists divide into camps. Optimists say, technology solves problems. Life is adaptable. Humans are ingenious. We'll figure it out as we go, developing solutions to problems as they arise. They point to human history of expanding into hostile environments, the Arctic, high mountains, deserts, and surviving through innovation. Pessimists say we're evolved for one planet and can't escape that. 300 million years of vertebrate evolution in 1G can't be overridden. Low-gravity reproduction will fail or produce increasingly unhealthy offspring each generation. Radiation will cause genetic degradation faster than evolution can compensate. Closed ecosystems will suffer cascade failures. Isolation will break social cohesion. Mars colonies will be like Antarctic stations, places people visit temporarily but never truly settle. Realists say we don't know. We'll discover problems we haven't anticipated. Some will have solutions, some won't. We'll adapt where we can, fail where we can't. The first colonies will be experiments, and some experiments fail. People will die learning what works and what doesn't. The learning curve will be steep and paid in lives. What we do know is that Earth isn't forever. On geological timescales, Earth has been hit by asteroids that cause mass extinctions. Supervolcanoes erupt, causing global winters. The sun is gradually brightening. In about 1 billion years, Earth will be too hot for liquid water. In 5 billion years, the sun will expand into a red giant and consume Earth entirely. These are certainties. The only uncertainty is timescale. So the choice isn't stay safe on Earth forever versus risk expansion into space. It's risk expansion and possibly fail versus stay on Earth and definitely go extinct eventually. Staying on one planet is the riskier long-term strategy. But expansion doesn't guarantee survival either. It just changes the risks from certain extinction eventually to uncertain survival possibly. 20,000 years is the test. If we can make it 20,000 years establishing colonies across the solar system, we've proven human civilization can survive off Earth. We've proven the biology works, the technology works, the culture works. 20,000 years becomes the foundation for 200,000, 2 million, 20 million. We become a truly spacefaring species, with presence throughout the solar system and eventually beyond. But if we can't make it 20,000 years, if colonies fail before then, if reproduction doesn't work, if radiation proves too damaging, if supply chains can't be maintained, if culture can't preserve purpose, then we learn our limits. We learn that humans are earthbound, that we can visit space temporarily but can't live there permanently, that our biology and psychology require Earth conditions in ways we couldn't overcome. Either way, we learn something profound about what humans are and what we can become. And we only learn it by trying. The answer won't come from simulations or thought experiments. It will come from real colonies, real people, real generations living and dying in space, testing whether 800 generations can pass the baton successfully, or whether it drops somewhere along the way. That's the frontier of uncertainty. And we're about to cross it. They'll see what we were and what we became. And maybe that's enough. We go not because space welcomes us. Space welcomes nothing. We go because Earth taught us nothing lasts forever. Species evolve or go extinct. Staying still is choosing slow death. We go because movement, adaptation, growth, these are what life does. And 20,000 years isn't the end of that story. It's just the beginning.